Hello everybody, the IMO 2020 was held on 21st and 22nd September. The host country this year is Russia, but given the current travel restrictions around the world, the contestants actually took the exam in their respective countries. I'll go over the solutions of the day 1 problems, followed by a short discussion of the score distribution for these problems. For the first problem, we have a geometry problem. Consider the convex quadrilateral ABCD and P is a point in the interior. The following ratios of angles hold. We have this alpha here is to 2 alpha is to 3 alpha. And at the same time we have this beta is to 2 beta is to 3 beta. The statement of the problem is to prove that the following 3 lines meet at a point. Firstly, the angle bisector of ADP. Secondly, the angle bisector of BCP, and thirdly, the perpendicular bisector of the segment AB. For the proof of the problem, I'm going to let O denote the circumcenter of triangle ABP. As you might guess, I'm going to show that the 3 lines meet at the point O. Firstly, the perpendicular bisector of AB clearly passes through O, because O is the circumcenter of triangle ABP. Next, since this is the circumcenter of triangle ABP, the angle subtended at the center here is twice the angle of shown over here. So this angle is 4 beta. At the same time, look at triangle BCP. The angle BCP is given by 180 degrees minus beta minus 3 beta, and therefore is 180 degrees minus 4 beta. Since this is 180 degrees minus 4 beta, when added to the angle on the opposite over here, these two angles sum out to 180 degrees. This proves that the quadrilateral OBCP is a concyclic quadrilateral. Once we have this concyclic quadrilateral, we notice that this dark green triangle and this dark green triangle are therefore equal. This light green triangle and this light green triangle are also equal. At the same time, OP and OB, they are the radius of the circle for triangle ABP. So OBP is actually an isosceles triangle, implying that the light green and dark green angles are equal. In other words, OC is actually the angle bisector of the angle BCP, thereby proving that the second line, namely the angle bisector here, passes through O. A completely analogous argument will show that the angle bisector of ADP passes through O as well. So that is all for problem 1. I will do a discussion of what I think of this problem at the end of the video. For now, let us move on to problem 2. So in problem 2, we have an inequality problem. The real numbers A, B, C, D are such that A is at least B, at least C, at least D, which is greater than 0. And A plus B plus C plus D is equal to 1. And we are supposed to show this inequality here. So when we look at the problem, I think we agree that this power term here is quite nasty. But luckily, by the weighted A and GM inequality, we can replace it with something friendlier. On the right here, I have shown the general form of the weighted A and GM inequality for reference. And since A plus B plus C plus D equals 1, it can be taken as weights, and plugging into the inequality, we get this expression here. Therefore, it suffices for us to show that this inequality holds. And at the same time, because A plus B plus C plus D equals 1, we can write 1 in this form. This is a useful simplification because now all the terms on the left and all the terms on the right, they are all terms involving the power 3. So it is tempting for us to simply expand the left hand side and right hand side and see whether we can get a simple direct comparison of the terms. Now in doing the expansion, I have organized the coefficients in the table form here, which will help the argument in the next step. So the way to read the table is that the diagonal here is A cubed, B cubed, C cubed, and D cubed. And for the off diagonal term, for example, this is the coefficient for AB square. Whereas for this square here, that's the coefficient of A square B. So I've captured all the coefficients of this expression in this table here. And when we expand here, we have the a cubed, b cubed, c cubed, d cubed term. And then all the terms involving two alphabets, they have coefficients 3. And then we have plus 6 of the terms involving 3 alphabets. Now, because this term at the bottom here, this is strictly greater than 0, it suffices for me to show that all these terms in the left table is less than or equal to all these terms on the right table. And actually, the reason why we organize it in this table is as follows. We are going to look column by column. We see that because A is at least B, at least C, at least D, right? If we move one count of the coefficient from a lower row to an upper row, the new sum is, the old sum is less than or equal to than the new sum, because we are moving from a row with a smaller letter to a row with a larger letter. And this is how we are going to argue the left table is less than or equal to the right table. Namely, look at column 1. We can move one count of the 4 here to the 2 here. And this gives us 1, 3, 3, 3. In the process, the sum stays the same or increase. Similarly, look at the second column. We can adjust it by moving the 4 to the 1, the 2 to the 1, and we end up with 3, 1, 3, 3. In the process, the sum stays the same or increase. Same thing from the third column, we can move the 4 up to the 2 and the 3 to the 1 and the 3 to the 1, then you get 3, 3, 1, 3. And lastly, you can move the 4 to the 1 and the 4 to the 1 again and the 4 to the 2, and then we get 3, 3, 3, 1. So by adjusting the columns in this way, we showed that the left table is less than or equal to the right table. Then we plus this thing here at the bottom that is strictly greater than 0, and this is the proof of the simplified inequality in the middle of the slide. So that's all to problem number 2. It's actually not as complicated as you see. I'll do a discussion at the end of this video. Okay, let us now look at problem 3. This is an interesting combinatorics problem with a rather clever solution. There are 4n pebbles of weights 1 to 4n. Each pebble is colored with one of n colors, and there are 4 pebbles of each color. So that we can arrange the pebbles into 2 piles so that the following 2 conditions are both satisfied. Firstly, the total weights of both piles are the same. Second, each pile contains 2 pebbles of each color. Okay, so in solving this problem, we are actually going to do something slightly more restrictive, but it will be easier for us to come up with the solution to this problem. What we are going to do is we are going to call k and 4n plus 1 minus k as partners. So for example, 1 and 4n are partners, 2 and 4n minus 1 are partners, and so on. Now suppose I have 4 pebbles here of the same color. What we need to do is we need to throw 2 of them into pile A and the other 2 into pile B. And do the same for all the colors such that the 2 conditions here hold, right? Now suppose I can, to give us a concrete term, I'm going to say that I'm going to highlight 2 pebbles of each color. The highlighted pebble will be placed into pile A and the non-highlighted one will be placed into another pile B. Okay, so suppose I can perform the highlighting such that the partners are either both highlighted or both not highlighted. Then I claim that we have actually met the 2 required conditions of the problem. Well, obviously, each pile will contain 2 pebbles of each color because I highlight exactly 2 of the 4 pebbles of each color. As for the first condition here, why is it the case that the total weights of both piles are the same? Well, because partner pebbles either end up both in pile A or both in pile B. We see that what is pile A made of? Pile A will be made of pairs of partners. And how many pairs? There are n pairs of partners. There are no lonely pebbles inside because the partners belong together to the same pile. similarly for pile B, they are again all made up of pairs of partners. There are no lonely pebbles in pile B. And so therefore, all the 2n pebbles in pile B, they all pair up nicely with their partners, and there are n pairs of partners in pile B. So pile A and pile B have the same number of pairs of partners, and each pair of partners sum up to 4n plus 1. So you see that this is a slightly more restrictive condition than the initial condition, but it will help us set up the problem in a clever way. So on this slide, I have placed the condition that we want over here. We want to highlight 2 pebbles of each color such that partners are either both highlighted or both not highlighted. So over here, I've put together a graph H. The graph H has vertices being the pebbles. So we have 4 vertices here, and now 4 vertices here, and so on. And the H indicates partners. So I draw an H between 2 vertices if and only if they are partner pebbles. So what we want is we want to highlight 2 vertices in each super vertex such that the edges, right, they either incident to both highlighted pebbles or both not highlighted pebbles. Okay, so to do this highlighting process, what I will do is I will consider a supergraph G. So a supergraph G is formed by collapsing the 4 pebbles of a color into a super node. So we have a super vertex, in other words. So the super vertex, right, the edges will just collapse accordingly. So for example, there will be one edge from this super vertex to this super vertex and so on. And yes, this is a multigraph, meaning that, for example, from this super vertex to this super vertex, there will be 2 edges between them. And also loops will be allowed. If let's say a pebble is partnered with a pebble of the same color, then the edge will collapse into a loop between the super vertex to itself. Okay, so when we look at this supergraph G, we notice that each super vertex has degree 4. What this means is that for each connected component of the supergraph, we are able to produce an Eulerian circuit using the edges. Eulerian circuit, if you recall, is a way to go around the graph so that we travel on each edge exactly once. And why is this useful? Well, once we have the Eulerian circuit, what we are going to do is we are going to look back down at the level of the pebbles, and we are going to move along the Eulerian circuit. Let's say this is the first edge of the circuit, and then this is the second edge of the circuit, and then this is the third edge of the circuit, and so on. What we'll do is we'll alternate between highlighting the edges and not highlighting the edges. So highlight, don't highlight, highlight, don't highlight, and so on. So we, by construction, when we highlight the edge, we will highlight both the pebbles at the endpoint. So by construction, partners are either both highlighted or both not highlighted. Now, we also need to check that through this process, we will end up with exactly 2 pebbles that are highlighted and 2 pebbles that are not highlighted of each color. And this is quite a straightforward thing to check. So, for example, when we have incoming edge, this will be followed by an outgoing edge. We have one of them is highlighted and the other one is not highlighted. So each highlighted one is paired up with each not highlighted pebble. Well, there could be cases where we have a loop, but for the loop, we notice that the loop, right, will have will result in both highlighted or both not highlighted, but the edge that is coming in and going out immediately after that, they will be of the same highlighting status. So anyway, this is something that you can reason it through yourself, and I think you should be able to convince yourself that this process will result in exactly 2 pebbles of each color being highlighted. So this is actually all for this problem. It sounds a bit complicated, but actually once you understand what is happening in the graph, you realize that this is actually quite an elegant solution. So lastly, I will talk about the statistics for these 3 problems. We see that for problem 1, the average got a little bit higher than the previous 2 years. And actually, if you think about the solution I presented, it's quite a short solution with not that many complicated steps. So it may seem that the problem is actually easier than past years, but the tricky part is you need to first guess that O is the point where the 3 lines meet. Actually, initially when I did this problem, I came up with an alternative solution, which I think is more intuitive, and this could be why the problem is people did better on this problem than previous years. So the way I approached this problem initially is that I define a point E here so that I can split the angle 3 alpha into alpha and 2 alpha. In that way, I have alpha alpha giving me an isosceles triangle, and at the same time we have 2 alpha giving me another isosceles triangle, which seems very nice and something intuitive to do. And this gives the angle bisector here, converts the angle bisector here into the perpendicular bisector of PE. So similarly, by splitting into beta and 2 beta here, the angle bisector over here is the same as the perpendicular bisector of PF. So what we have is we want to show that the perpendicular bisector of PE and PF and the perpendicular bisector of AB, they all meet at one point. Well, we have 2 perpendicular bisectors here, so that means these 2 perpendicular bisectors will definitely meet at the circumcenter of PEF. And the whole problem reduces to basically showing that AEPFB, they are concyclic, and with a bit of angle chasing and length chasing, we can show it quite easily. So I won't go through the details, but this is, I think, putting a point E and F here to split the angles are something that is one of the first things you might try, and it does lead to a solution. So this could be an alternative solution that many of the contestants could possibly have produced. Now let's look at problem 2. So problem 2 got slightly harder than previous years, and we noticed actually there's quite a number of contestants that obtain a partial score of 2. So I'm not sure how they got a partial score of 2. One suspicion is that they managed to apply the weighted AMGF inequality and reduce to this inequality here, but I'm not too sure of the marking scheme. But anyway, I think this problem, I would say it might seem difficult because the steps are not something that can be easily motivated, but once the steps are presented to you, they actually there is a aha. Actually, in retrospect, they seem like quite obvious things to try. So what I mean is, for example, the weighted AMG inequality, in retrospect, yeah, it seems quite obvious that we should have applied this to get rid of the powers and simplify into this, and writing 1 as this cube expression here is something that seems quite that takes a bit of inspiration to come up with. But once someone tells you that this is the thing to do, again you will be like, aha, I should have considered this because that will make me have terms of power 3 comparable to terms of power 3. Once we reach this intermediate inequality step, I think a brute force expansion of terms on both sides is something quite natural to try. So the main hurdle, I would say, is writing 1 as this expression here. And now for problem 3, actually the average got up slightly compared to previous years. Of course, it remains the most difficult problem of day one. And I would say that the main difficulty is around organizing the problem in a way that is more tractable and more concrete. So once you are able to organize the problem in terms of this graph theory formulation, right, actually it's not too difficult to come up with the solution. If you notice there's actually like only like mainly two steps into this problem, which is you formulate the idea of a G and a H, and then you consider how do you form an Eulerian circuit and do the highlighting appropriately. So there are not many super long steps involved, but each step takes a bit of ingenuity. So this is why the problem is difficult, but I wouldn't say it's one of the hardest problem tree of the IMO. So that's all for this video. I hope you enjoy it. I will come back soon with the day 2 solutions and discussion of the score distribution. So stay tuned and hope to see you soon.